pressure on the upstream side of the valve is sufficient to overcome the force of the spring, pushing the piston away from the seat and allowing flow through the valve. Flow in the opposite direction lets pressure work with the spring, closing the valve and blocking flow.
Pressure control valves, also known as relief valves. The function of a relief valve is to provide protection to a hydraulic system so that the system components do not malfunction, seize or burst, and the fluid lines do not burst or leak at the connections. The relief valve performs this function by providing a means for system fluid to be diverted to the reservoir when the valve pressure setting is reached. The opening of the relief valve is accomplished when pressure of the fluid in the system exceeds a pressure set by a spring force in the relief valve. The spring holds the relief valve in its closed position. As the fluid pressure rises to a level that exceeds the force of this spring, the relief valve opens and creates a flow path to the reservoir. This action results in the relieving or limiting of fluid pressure in the system to the value of the spring force in the relief valve. Figure 99 illustrates the basic direct-acting relief valve where either a ball or a poppet is held in the closed position by an adjustable spring. This blocks the flow path to tank. This valve can be adjusted manually. When pump pressure, P, exceeds spring tension, the valve is forced off its seat, allowing oil to flow directly to the tank. T, thus reducing or relieving system pressure. Simple pressure relief valve, cracking pressure. Figure 100 above shows a simple relief valve in the cracking pressure position. The simple relief valve, also called direct-acting relief valve, is kept closed by spring force. The spring tension is set to the relief pressure setting. However, the relief pressure setting is not the pressure at which the valve first begins to open. When a condition develops that causes a resistance to the normal oil flow in the circuit, excessive oil flow causes the oil pressure to increase. The increasing oil pressure is sensed at the relief valve. When the force of the increasing oil pressure overcomes the force of the relief valve spring, the valve moves against the spring and begins to open. The pressure required to begin valve opening is called the cracking pressure. The valve opens just enough to allow excess oil to flow through the valve. Simple pressure relief valve, relief pressure setting. An increase in the resistance to oil flow. Figure 101 increases the volume of excess oil and increases the circuit pressure. The increase in circuit pressure overcomes the new spring tension and further opens the relief valve. The process is repeated until the maximum volume of oil, full pump flow, is flowing through the relief valve. This is the relief pressure setting. The simple relief valve is commonly used where the volume of excess oil flow is low, where there is a need for a quick response. This makes the simple relief valve ideal for relieving shock pressures or as a safety valve. Pilot-operated relief valve. The pilot-operated relief valve, figure 102, is often used in systems that require a large volume of oil and a small differential between the cracking pressure and the full flow pressure. In the pilot-operated relief valve, a pilot valve, simple relief valve, controls the main unloading valve. It is much smaller and does not handle the large volume oil flow. Its spring is much smaller, allowing more precise pressure control. The difference between the pilot valve cracking and maximum pressure is minimal. The unloading valve can handle the complete pump flow at the designed maximum relief pressure. It uses system oil pressure to keep closed. Therefore, the unloading valve spring does not need to be strong and heavy and allows a more precise opening. Pressure. The system oil flows into the relief valve housing through the unloading valve orifice and fills the unloading valve spring chamber. The oil in the unloading valve spring chamber contacts a small area of the pilot valve. This allows the pilot valve to use the small spring to control the high pressure. When the oil pressure increases in the system, the same pressure is in the unloading valve spring chamber and the oil pressure is the same on both sides of the unloading valve. The combined force of the oil pressure in the unloading valve spring chamber and the spring force on the top of the unloading valve is greater than the force of the oil pressure against the bottom of the valve. The combined force in the spring chamber keeps the unloading valve closed. Open position. when the system oil pressure exceeds the pilot valve spring setting. Figure 103. The pilot valve opens. The open pilot valve allows the oil in the unloading valve spring chamber to flow to the tank. The pilot valve opening, orifice, is larger than the unloading valve orifice. Therefore, oil flows past the pilot valve much faster than through the unloading valve orifice. This allows the pressure to decrease in the unloading valve spring chamber. The force of the higher system oil pressure moves the unloading valve against the spring. The excessive pump oil flows through the throttling holes in the unloading valve to the tank. The throttling holes allow the unloading valve to dump the volume of oil necessary to maintain the desired relief pressure. Flow control valves. Flow control consists of controlling or regulating the volume of oil flow in or out of a circuit to a rate which is below that of the system pump output flow. Controlling flow in a hydraulic circuit can be accomplished in several ways. The most common way of controlling flow is by installing an orifice. When an orifice is installed, the orifice presents a higher than normal restriction to the pump flow. The higher restriction increases the oil pressure. The increase in oil pressure causes some of the oil to take another path. The path may be through another circuit or it may be over a relief valve. There are 4 basic types of flow controls. These are non-compensated flow controls, flow dividers, pressure compensated flow controls, temperature compensated flow control, non-compensated flow controls. The simplest type of flow control is the non-compensated flow control. Non-compensated flow control valves are used as restrictors to control the rate of flow into a branch circuit at a given input pressure to the valve. As system pressure increases, flow through the non-compensated flow control will increase with a corresponding increase in pressure drop. If outlet or load pressure increases, flow may decrease proportionally. The simplest form of a non-compensated flow control is an orifice. An orifice can conveniently be inserted into a hydraulic line as a standalone valve, or more typically, into a hydraulic fitting as a means of restricting the flow into a branch circuit. Needle or Glock type valves are also commonly used as simple flow restrictions that control the flow into a branch circuit. An orifice is a small opening in the oil flow path. Flow through an orifice is affected by several factors. 3 of the most common are: 1. The temperature of the oil. 2. The size of the orifice. 3. The pressure differential across the orifice. Temperature. The oil viscosity changes with changes in temperature. Viscosity is a measurement of the oil's resistance to flow at a specific temperature. Hydraulic oil becomes thinner and flows more readily as the temperature increases. Orifice size. The size of the orifice controls the flow rate through the orifice. A common example is a hole in a garden hose. A small pinhole will leak in the form of a drip or a fine spray. A larger hole will leak in the form of a stream. The hole, whether small or large, meters the flow of water to the outside of the hose. The amount of water metered depends on the size of the hole or orifice. The orifice size may be fixed or variable. Check valve with a fixed orifice. Figure 104 shows an example of a check valve with a fixed orifice that is commonly used in construction equipment. The fixed orifice is a hole through the center of the check valve. When oil flow is in the normal direction, the valve opens and allows oil to flow around the valve as well as through the orifice. When oil attempts to flow in the reverse direction, the valve closes. All reverse flowing oil must flow through the orifice that controls the flow rate. Variable orifice. Figure 105 shows a variable orifice in the form of a needle valve. In the needle valve, the positioning of the valve tip in relation to the valve seat changes the size of the orifice. The oil flow through the needle valve must make a 90 degrees turn and pass between the valve tip and the valve seat. The needle valve is one of the most frequently used variable orifices. When the valve stem is turned counterclockwise, the orifice becomes larger and the flow increases through the valve. When the valve stem is turned clockwise, The orifice becomes smaller and the flow decreases through the valve. Figure 106 is an example of how a variable orifice can be used to control the operating speed of the cylinder. Flow dividers. Flow dividers are either gear type or spool type. Their function is to divide the flow into two different streams. These two streams typically are equal in flow rate, i.e., each stream is half of the available flow. However, through the use of springs and spool design, or the use of different gear displacements, it's possible to obtain different flow ratios for the two flow streams. Gear-type flow dividers, figure 107, are similar to a double, or triple or more, gear motor. They use a common inlet and stacked gear sections that are maintained at the same rotational rate by a common shaft. By this means, the incoming flow is divided into a stream of flow for each gear section. It is possible to have more than two sections to produce more than two flow streams. The volume of flow from each stream will be affected by the volumetric efficiency of each gear. Section. Spool-type flow dividers, figure 108, are more commonly used as they are typically more convenient to install in the hydraulic circuit, or can be integrated into the outlet cover of a pump. Their design is such that they provide either proportional output flow streams or a priority output flow stream when used as a priority valve. The priority flow stream provides a set rate of flow while the secondary stream provides only the flow that is available after the priority stream has been satisfied, when the accuracy of the output flow streams is critical to the application. A pressure compensation feature can be added to the spool-type flow divider in order to prevent changes in output flow rate as inlet or outlet pressure changes. Pressure compensated flow controls. Pressure compensated flow control valves are used to provide a constant output flow rate into a branch circuit regardless of system input pressure or load pressure. They can be either piston type or spool type. In both cases, constant output flow rate is achieved by using springs to maintain a constant pressure drop across the metering orifice. As input pressure increases, output flow is restricted as either the piston or spool is closed off. This prevents an increase of output flow as the increase of input stem pressure tries to force more flow through the valve. Figure 109 illustrates a bypass-type pressure compensated flow control with integral relief valve. The difference is the output flow is controlled by an orifice inserted in the regulated output line. This line maintains a constant flow to a work circuit, all excess flow being diverted to the reservoir through the tank line. As the workload increases, pressure in the output line increases, as does the pressure in the spring chamber at the right side of the hydrostat piston. Inlet pressure to the left of the hydrostat piston will also increase to a level sufficient to overcome the pressure at the right of the hydrostat, plus the value of the spring. At this point, the hydrostat will slide to the right, allowing the excess flow to exit through the tank port. Thus, regardless of the pressure on the right side of the hydrostat, the pressure on the left will be above it by virtue of the spring value. It is this constant pressure drop across the orifice that maintains the pressure compensated flow to the regulated outlet. If the regulated outlet pressure exceeds the pilot spring setting inside the hydrostat, the pressure in the spring chamber will be limited and the valve will function as a relief valve. Figure 110, an alternative design. Output flow is controlled by an orifice in the main spool. The spring at the right of the spool maintains a constant pressure drop, and therefore a constant flow across the orifice, and excess flow is diverted to the excess flow port. A separate relief valve protects the regulated flow circuit. Bypass pressure compensated flow control valve. Figure 111 shows an illustration of a bypass-type pressure compensated flow control valve. The bypass-type pressure compensated flow control valve automatically adjusts to flow and load changes. The amount of flow through the valve depends on the size of the orifice. Any change in oil flow through the orifice creates a change in pressure on the upstream side of the orifice. The same pressure change acts against the dump valve and spring. When the pump flow is within the design flow of the orifice. The force of the upstream oil pressure acting on the dump valve is less than the combined force of the downstream oil pressure and the spring. The dump valve remains closed and all of the pump oil flows through the orifice. When the pump flow is more than the desired flow of the orifice, the force of the upstream oil pressure acting on the dump valve is greater than the combined force of the downstream oil pressure and the spring. The dump valve opens and the excess oil flows through the dump valve to the tank. Combined orifice and dump valve. The more common type of flow control valve is shown in figure 112. This valve combines the action of the orifice and dump valve in one moving part. The pressure compensating operation is the same as the bypass pressure compensated flow control valve. The graphic on the left shows flow through the valve that is either of the flow rating or less than the flow rating of the valve. The graphic on the right shows that flow is beginning to exceed the flow rating of the valve. The pressure differential resulting from the flow across the orifice becomes great enough to begin compressing the spring and start dumping the excess oil as shown. If the flow through the valve increases, the action of the orifice will cause the spring to compress still more, and more flow will be dumped. The controlled, metered flow remains fairly constant as flow to the valve increases or decreases. Temperature compensated flow controls. Temperature compensated flow control valves are used to maintain a constant output flow rate where a change in the fluid temperature would cause a change. Temperature compensation is usually accomplished through a variable orifice that is controlled by temperature sensitive by metallic lever or rod. Graphic symbols, valves. The basic directional control valve symbol. Figure 113 consists of one or more basic envelopes as seen in the top row of symbols. The number of envelopes used represents the number of positions that a valve can be shifted to. Shifting and valve positions will be discussed in more detail later. Next are valve ports, or the connection points for inlet, outlet, and working lines. The first symbol to the left has 2 ports and is commonly referred to as a two-way valve. Not to be confused with a 2-position valve as seen in the middle of the top row. Valves may have as many positions or ports as needed, although most are in the range of 1 to 3 positions and 5 or fewer ports. The other 2 symbols represent the typical port arrangements for 3 and 4-way valves. The terms 2, 3, and 4-way valve does not necessarily mean the valve will have 2, 3 or 4 ports, but rather designates the number of ports flow is occurring between. An example of this will be seen later after discussing internal passages next. Normally blocked. Lines and arrows inside the envelope are used to represent flow paths and direction between ports. Figure 114. 2 basic types of valves are seen here, normally blocked and normally open. These terms represent the internal flow condition of the valve in its neutral state. Valve symbols are always drawn in their neutral or unactivated position. Valves which change position due to flow or pressure are in their neutral condition when there is no flow or pressure in the circuit. That is, the external lines are connected to the ports of the envelope with internal passageways. Representing the valve's neutral condition, the shifting of valve spools or envelopes using graphic symbols must be done with your imagination. In full machine schematics, components are always drawn in their neutral position. Later, we will see an example of how symbols should be shifted using your imagination. The top row of symbols represents 1, 2, and 3 position valves in which flow is normally blocked in neutral, while the bottom row of symbols depict 1, 2, and 3 position valves which are normally open to flow in their neutral position. Let's take a closer look at the top row of symbols to further understand the internal flow conditions. The first symbol seen to the left in figure 115 represents a normally closed infinite positioning valve. This means the valve spool can be shifted either partially, in an infinite number of positions to meet the flow through the valve, or fully open. The arrow here denotes flow is normally in one direction, from the top port to the bottom port. The middle symbol in figure 115 represents a 2-position normally closed valve. The function of this valve is very similar to the function of the valve just discussed. But rather than allowing infinite positioning of the valve spool to meter flow, this valve is either completely closed or fully open. In the neutral position, flow is blocked, indicated by the small "it" symbol. In the fully open position, as shown by the right-hand envelope, flow is allowed in either direction. This is denoted by the two-headed arrow, compared as to the previous symbol in which flow was only in one direction, denoted by a single-headed arrow. The symbol seen to the right of figure 115 represents a normally closed three-position valve. The far left envelope shows that when the spool is shifted right, connecting the flow paths in the left enclosure with the external port lines, parallel flow is allowed between the valve ports. The far right envelope shows cross flow is achieved between the ports when the spool is shifted left. Typically, whenever a valve symbol is shown by itself, the ports are labeled to denote supply, return, and working ports. But when shown as a part of a complete circuit schematic, the connecting lines must be followed out to determine which ports are the supply, return, and working ports. 2, 3, and other multiple position valves can also be shown to have infinite positioning or flow. Metering capability. This is done by the addition of two horizontal bars drawn parallel to the valve envelopes, as will be seen in the next slide. Valves drawn with only one envelope, as previously seen, are assumed to have infinite positioning capability and do not require the additional horizontal bars. Shown to the left of figure 116 are partial cutaway drawings of directional four-way control valves in their neutral positions. Seen to the right are the symbols for only the centered or neutral condition of the valves. The labeled port abbreviations are P supply from pump, T return to tank, a work port, B work port. The valve cutaway to the upper left contains an open-centered type spool. Supply flow from the pump is unrestricted to either working ports A and B or return to tank. In this case, supply flow will take the path of least resistance. The symbol to the right indicates that all ports are tied together. Junction dots which would allow unrestricted flow between any of the ports. The cutaway in figure 117 represents a closed center type spool. Pump supply flow is blocked by the spool lands and valve housing to the right and left of working. Ports A and B. Ports A and B are also blocked by the spool from draining the tank. The symbol to the right utilizes small T crossed lines to denote flow is blocked internally on all 4 ports. 2 more examples are seen here of valves and their related center position symbol. The top cutaway and symbol is representative of a closed center motor spool in which ports A and B are both open to tank while pump supply is blocked. The symbol to the right shows that ports all and B are tied together and drain to tank, while pump supply is blocked. The lower cutaway and symbol are representative of a tandem type open center valve. Pump supply is open to tank by means of a passageway inside of the spool, while ports A and B are both blocked. The symbol to the right shows the pump supply port is tied to tank return and ports all and B are blocked, although nothing from the symbol shows it's done by means of a hollow spool. Once again, you must keep in mind symbols are used to represent the component's resulting function, not necessarily the component's construction which achieves this function. This valve is referred to as a tandem type valve because rather than having pump flow go directly to tank through port, it could be diverted to another valve section from port. Therefore, the 2 valve sections are in tandem or series, one behind the other, the second valve being fed by the return oil of the first. An example of this type valve arrangement will be seen later. Pressure control valve. The symbol in figure 118 shows a single valve envelope which is normally closed to flow. It also shows that system pressure is sensed through the pilot line and works against a spring, tension which can be varied. Nothing from the symbol identifies whether the relief has both a pilot and relief pocket. All that pressure is sensed through an Orifice. Graphics sysmbol flow control valves.